Good to go?
Mm-hmm.
Okay.
Just wait 1 minute and let's start after that. Okay, howdy everyone, and welcome to our Texas A&M R&D series. My name is Sergey and I'll be a moderator for today's presentation. A few comments for participants. Please keep your microphone muted. Participants are encouraged to start typing questions during the presentation, and I will pull out this question to the speaker during our Q&A session. And today's topic of the webinar is mechanical earth modeling. And our speaker is Issa Haddad. Issa Haddad is an acoustic and geomechanics petrophysicist in Schlumberger. His work includes anisotropy characterization and 3D mechanical properties interpretation for unconventional and conventional basins. Issa Haddad graduated from Texas Tech University with a Master's of Science degree and received his Bachelor of Science degree from Al-Bat University, both in petroleum engineering. He is currently pursuing a Master of Science in Data Science and Analytics from University of Oklahoma. His interests include utilizing the machine learning tools in predicting Thompson parameters, as well as 3D geomechanics model. And he is an active member of SPWLA and SPE. So Issa, I think you can start.
Hello everyone, and thank you for joining us today for this webinar. First, I would like to thank SPE chapter of University of Texas A&M for inviting me, and I would like to thank you all for joining us today for this webinar. And I hope it will be a good hour and a half, very fruitful for both of us to share our knowledge and have a meaningful discussion. Our topic for today is mechanical earth model, and our agenda for today will be the definition of MEM, mechanical earth model, the workflow, or where we can use it, why do we use it, and in the lifespan of the well, where it's applicable. Then we will have a brief definition of stress and strain before we dive into the computation of overburden, how to compute it, its definition, and then the photo pressure. From there, we will also define elasticity very shortly and speak about dynamic and static elastic properties and well logs and how we can use them in our MEM and what kind of information do we need. Then we will jump to the rock strength, define the UCS and the friction angle, and also the tensile strength. And then we'll talk about stress magnitude, stress direction, and then we will conclude our meeting and have it open for question and answer. So for the mechanical earth model, it is comprised from different elastic properties, stress, physical strength, and also pore pressure, vertical stress, and minimum and maximum horizontal stresses, and of course all their direction with respect to each other. Based on the level of complexity of the model, we can start from 1D, 2D, 3D, and even including the time, how the stress change in time, and have it in 4D. If our model will be honoring faults and conformities and other complex geological features, we will need a fully prepared model in a 3D modeling tool such as Petrel. But in our case today, we'll be talking specifically about 1D MEM, which is a borehole geomechanics, and how we prepare that. For wellbore stability, goals for fracture stability, for sanding production issues, and among other challenging that occur during drilling and explorations. What I like to define here, the mechanical stratigraphy. Mechanical stratigraphy, it is simple as just dividing your rock between shale and non-shale. That can be for a simple lithology. We can use just a gamma ray flag. For a more complex lithology, we can use full elemental analysis to help us deselect the proper equations and the proper methods for our MEM. The end product is described on the right side of this the slide, the elastic properties, the rock strength, and based on the stress regime, we will get vertical stress, maximum horizontal stress, minimum horizontal stress, and pore pressure. They're not always in this order. That is a function of the stress regime and the region that we're taking the study at. And of course, we will need always to know the stress direction at any given point for our drilling purposes. Our model is, or our workflow will always start from data audit. We will always, based on the objective of this model, we will try to get all the data we need and see what we have, where we have it, and where it's missing. For our case, since it's 1D MEM, we will look at well logs, we will look at drilling reports, see whether they have kicks, whether they have losses, what was the mud weight usually for most overbalance drilling operations. The mud weight is supposed to be a little bit above the pore pressure to stay in a safer drilling operation if that's the purpose of being overbalanced. Unless the formation is very stiff and competent, then they can drill it under balance and they know it's not going to flow back on them. Once we have the data audit done, we move to the mechanical stratigraphy that we defined as either shale and shale, or if we are in 3D, faults and formation dips and so on. Then we move to the overboard and stress computations from density log. And then we try to model the pore pressure in shales. And if we have calibration points from non-shale formation like sands or limestone, then we can use that as well. Once that is done, we move to the elastic properties from the compressional and shear slownesses and bulk density. Once we have that done, we move to the mechanical properties. I always like to finish the quantitative qualities that we need. So then we do minimum stress, maximum stress, and we can do the stress direction independently, because at the end of the day, the direction is not a number. It is just our knowledge of it and how we will design our work, knowing this stress direction, how we will design our completion, how we'll design our frac work or whatever we're planning to do. And finally, we will take all this MEM. So at knowing the stresses and their orientation, the MEM is over or it's done, but the MEM itself is the bulk input for wellbore stability analysis, plane of weakness, you name it, whatever application there is in the lifespan of the well, the MEM is part of it. So why do we care about the MEM? The MEM, it is the primary tool to reach our goals of producing hydrocarbons safely during the lifespan of the development and production. Without it, we can see during the drilling, we can see so many incidents, kicks, and loss of the tools in the borehole, among so many other challenging things that can be life-threatening. But also during the production, after we are done drilling, we also have subsidence issues, and we have caprock integrity problems, and we have water flowing and all that. So overall, we need the MEM in order to achieve our goals safely and with a cost-effective manner. And here in this slide, I'm just showing you that geomechanics work starts from the moment we put the drilling rig up till we abandon the well. So you can see well bore instability issues, lost circulation in a fracture reservoir, the production of undesired fluids, optimized completion, optimized stimulation. So pretty much it is all over the lifespan of the well. So here it's just a simple introduction to stress. Stress is defined as load over area. That is the definition, whether you are on in the earth, in geomechanics, or if you are on the surface level. And in any cube or any particle, there are 3 different stresses applied to it from 3 dimensions. And due to the difference in magnitude between those stresses, each one of them will pull the body under compression in a different way that generates also different shear stresses. So we will end up with 3 normal stresses and 6 to 9 shear stresses. And due to the complexity of the geomechanics work when it comes to new exploration, working or trying to define 9 entities or more will be very challenging. So to overcome this issue, the geomechanics community came to agreement that we can define the stress state near the surface or at any point by knowing the 3 normal stresses and their direction in space or in direction acting at the point of interest. So in this case, what we're trying to do, we're trying to eliminate the shear stresses and try to work with the principal stresses only. And as we define the stress when we are applying a stress on a body, so for example, most of the work will be unless the cutting that happens by the drilling bit, most of the stresses that are applied during our work will be mostly compression. And once we compress the rock in one direction, there will be a shortage that will cause the shrinkage in the dimension of the stress, but also the rock will expand a little bit in perpendicular. So the change in magnitude is the strain with respect to the original magnitude, and the change in magnitude with respect to the stress direction when in a ratio to the increase in width, that is pretty much Poisson's ratio that we'll talk about later. That is one important parameter that we look at in the geomechanics workflow. And as the stress, we reduce the problem dimensions by only considering principal stresses. Also, the same thing applies to strain, where we can only work with principal strains, and yet we are able to define the stress and strain state when we need to. So moving to the overburden and the put pressure computations. The overburden, it is pretty much, or if you want to simplify it, it's just the weight of the at any depth point in the well trajectory. It is just the weight of the overlaying formation and fluid filling those formations. So in this case, if you are offshore, at any point, the overburden is the weight of the rock and the water level or the water thickness above it. If you're on land, then it's just the weight of the overlaying rock and fluid. So pretty much from the bulk density that we measure in wireline acquisition. When we are computing the overburden, we usually try to have, or that's what we desire always. We want bulk density, because bulk density is measuring both the rock and the fluid filling it. And we try first to extrapolate when we don't have the bulk density to the surface. It will be amazing if we have bulk density to the surface, but most likely you'll have it on 2,000 or 3,000 feet in a very long and deep well. So what you will need to do first, you need to run your TVD computation, because when you are running a gradient, overburden gradient here, and your end goal is a PSI per foot, you will always need to work with true vertical depth, just like when you are computing the temperature gradient and so on. So what we do, it's a very simple and mostly automatic approach. When you're using any of the commercial softwares, you define what you think is representative value for your bulk density at the top of the locked interval, and what is a representative point at the very bottom of that interval. And then you, based on your solid on the surface, when you get probably from your mud logger, you get a value for your density at the surface. And the software will automatically extrapolate for you the density value. So you will have a synthetic density from top to bottom. And then the stress is computed just by the integration of that bulk density over the entire depth interval multiplied by the gravitational acceleration constant. So it's pretty straightforward computations. There is no right or wrong way. There is no validation to it. That's the drawback. You know, for pore pressure, we have validation. For minimum horizontal stress, we have DFIT. But when it comes to vertical stress, it comes that your local knowledge and your local expertise is the best judgment. For example, any value in Wolfcam Permian Basin above 1.08 will be too high, and any value above 0.8 in the Gulf of Mexico at 20,000 feet, that will be also too high. So you want to always validate your results with an actual validation tools like core, but since we just said there's no validation for this one, we'll always try to get your best estimate from a local or expert in the region. Moving to the pore pressure, and the pore pressure is a topic itself. We can spend days on it just trying to talk, but in a nutshell, the pore pressure for permeable and porous rock is the pressure that is generated by the fluid in a formation. So if you're in sandstone, the sandstone has 20% porosity filled with the fluid is expressing pressure on the grains of the rock. That is the pore pressure. That is actually the reservoir pressure. This answer that is very simple for us in those conditions can be very challenging to know in unconventional rocks and in the source rock, like shales, due to their complexity, their small pores size, their chemical structure, the presence of bond water on the surface of the shale. So, and also being in equilibrium with a thick sand above or below, that represent a drilling hazard for us. This is why when we try to come up with solution in those shales, you know, they're small, they don't usually flow on us, but once they are in equilibrium with sand for so long, the sand has a high porosity. That sand is overpressured, and once you go in, if you are not prepared with the proper mud weight and so on, then you'll have a flow back on. The nature of shale, the way it compacts over time, the reduction in porosity and so on, it allows us to model it actually, to model the pore pressure. In permeable formations, we can measure it, we can't model it, but the shale itself, it allows us to model the pore pressure and have a good estimate. And also recently I've seen and talked to clients where they had actually stabilized, they had actually measured the pore pressure in shale by stabilizing the pressure transducer in the tool like MDT or so on, something similar from different vendors. They stabilize it for a month within a 5 psi above and below, and then they call it, this is our pore pressure. It's also a very good approach, but it takes so much time, and sometimes we don't have that luxury. Pore pressure, we will need it for drilling optimization. If you are unaware of your pore pressure and you have a high mud weight, first of all, your rate of penetration is lower because you are using excessively high mud weight. There's a good chance that you may fracture formation and have losses just because you really don't know what is the mud weight and you're trying to be safe. And of course, if you are drilling with your purpose is to be overbalanced, but yet you are underbalanced due to the lack of knowledge of the pore pressure, and also you will end up with having flow back and possible kicks. So knowing the pore pressure is a must for drilling purposes, and also to for other reservoir characterization work. So how do we measure it, or how do we model it? Because I said we can model it in shales. So using some of the measurements like the compressional slowness and the deep resistivity, formation resistivity, or the EDC from drilling, you can use a graphical method such as Eaton. Eaton is probably the most famous method for determining the pore pressure. And the way the method works, it will automatically create for you a baseline. Once you divide your lithology between shale and non-shale, the method will automatically create a baseline for you and compare at every depth point for compressional slowness or for resistivity the value with what the value would be if the pressure was normal. At the end of the day, what you're trying to do, we're trying to look for the normal compaction trends. That's what you are trying to do, which is something can be very, very challenging. And sometimes if you're logging only 1,000 feet of a log, then there's a good chance that you are just looking at a thick shale with that could be all over overbalanced. And in this case, you have no means of determining the normal compaction trend. So here, what I'm showing you is what we just said. We first define where we can compute, where we can model it, and where we can't. So in this case, I divided between sand and shale, and then in using the compressional slowness, I draw the line that I think is the normal compaction line. Once the compressional slowness is, once the rock becomes slower, that means we have an overpressured zone. And here I compared my results to the mud weight. My results in this case fit very well. And you can see the line it's not vertical, it is increasing a little bit. That's under a valid assumption that the rock becomes stiffer as you get deeper in the well. So this is one method to define it. I personally like this method to see, play around and see what affects the results and whatnot. But overall, if you're working in a project and the consistency is something that you're looking for, then in this case, I would go with different method just because graphical solutions are not always consistent. We draw things differently. So that's why for this approach, there is Bauer's method that is exactly created to overcome what I just mentioned. And it's pretty simple power law equation that you need only to feed the change alpha or A and B as parameter. And from there, once you change A and B, the method will compute the pore pressure for you. From your input will be vertical stress, and the method will, from the effective pressure, will back calculate your pore pressure for you. So this method is consistent. You can give the equation to a colleague of yours, and the results can be consistent among you and among other wells. For the elastic properties, if you want to define the elasticity, it is just very simple, reversible behavior, which is for other than the earth, it should be considered, or it's usually considered a linear quality. But when it comes to the rock, it is a nonlinear quality. And when we are working geomechanics, we use Young's modulus and Poisson's ratio for our elastic property calculations for an isotropic rock. So we get one Young's and one Poisson's ratio. And to get to Young's modulus and Poisson's ratio, we will need the shear modulus and the bulk modulus. The shear modulus is a measure of how the solid or any point of the borehole is resisting the change in shape. When we are applying the force on it, how does it resist the shape? This is usually measured in a lab, and usually it's measured from the slope of the loading, when you are applying the load on the sample. But since we don't have that means in a wireline acquisition, after of course a lot of research, that the shear modulus magnitude has been determined in a correlation between measured bulk density and shear slowness. And for the constant value here, the numerical part is just a function of the unit system that you're using. So for bulk density in gram per cc and shear slowness in microsecond per foot, and an output shear modulus in MPSI or 1000 PSI, then this is the numerical value that we will use. Once we have the shear modulus from the bulk density and the shear slowness, we can compute the compressional or the bulk modulus. And it is a measure of how the rock would resist being under compression. And in the same manner, it is something we need from the lab, but we can compute from bulk density and compressional slowness, and of course including the shear modulus in the computations. Moving on to Young's modulus. The Young's modulus is the stress to strain ratio. The stiffer the rock, the higher the Young's modulus that it will have, and that means it's the rock will fail more than it will elong, or it will be the yielding zone for it will be a lot smaller. While the Poisson's ratio, it is the change in the so when you are applying a force on a rock or stress in the direction of F here, then as we mentioned, there will be a reduction in the longitude of that material, but in perpendicular direction, the rock will expand and the width will gain some small value. So Poisson's ratio is that expansion in the width divided by the change or the reduction in length when the force is applied in longitudinal manner. And Poisson's ratio for it will have an opposite correlation with Young's. So stiffer rock will have higher Young's modulus, will lower Poisson's ratio. And if we want to put Poisson's ratio in perspective to how the Earth is acting, so you have a vertical stress generated from the formations above your target, let's say at 3,000 feet. And the stress, the weight of those formations is acting on compressing the formation at 3,000 feet. If the formation has a high Poisson's ratio, that means there is a larger horizontal displacement because the vertical stress is pushing from the top and it's carried from the bottom, so the rock will expand horizontally. And this means it will have a higher Poisson's ratio. Of course, if the rock is a stiff rock, the rock is not gonna move that much. That means it has a low Poisson's ratio. And again, those qualities are computed differently in a lab, and now we are looking at dynamic elastic property. They're called dynamic because they are derived from a wireline acquisition where you have tool that generates waveforms logged in a well, and the tool is moving upward or downward, most likely upward at very high speed, 300 to 600 to probably 1800 feet per second. So the measurement is pretty dynamic and it happens very, very fast. But before we can use those in our computations, we need to account for this difference. I wouldn't say it's a problem because we can't always afford to have core in every single well. So for that, we will need to convert those, and mostly the Young's modulus. We need to convert the Young's modulus from dynamic to static. It's widely accepted in the industry that we only convert Young's modulus because Poisson's, on the other hand, is a very small values between 0 and 0.5 for all materials. So the change will be very insignificant. But when we come to addressing the stiffness of the rock, it's very important that we account for this issue. And as you can probably read it yourself, but always dynamic measurements are higher than static measurements. And that is because when the wireline tool is in the borehole and it's releasing the waveforms that's for the compressional and shear velocities, we are not applying as much stress on the rock as it is in the lab. And also we are looking at that same rock for a split of a second as the tool moves very fast. So all those parameters are accounted for using different static to dynamic convergent factors and equations. So for you guys, I've prepared a set of a table of the most used methods when we are converting from dynamic to static. I personally work mostly with modified Morales, and I've done so many wells with core calibration, and modified Morales worked very well for unconventional rocks. Here in this table, as you can see, we have the equation, also what we need as an input. Since we're only converting Young's modulus, that's the only thing we need. But also the suitability, where we can use this equation and what are the conditions that we will need to have in order for this method to work. At the end of the day, the way those are derived, it is by basin and by company. So let's say an X operator does a course study, and in the course study, they measure dynamic and static, and they get their equation out of 50 well. That doesn't mean, and they can publish it, and we will end up with more correlations like those. But that does not mean it's going to fit everywhere, because at the end of the day, it is very limited to the number of points have been considered into the study, into the original study. And I will give you an example on the fitability and also the misuse of equations in geomechanics in general. After we convert the Young's modulus and we say that Poisson's ratio is the same, we back calculate the shear and the bulk modulus, and we get the static values from them. Once we are in, we have our two modulus in Poisson and Young's in static format, then we can move to the UCS computations, the tensile strengths, and the friction angle. And in the same manner, here I'm providing you as well with a table with the most used methods for computing the unconfined compressive strength, and also what is required and if there is any condition to use them. I worked with McNally. I worked also with Plum shear modulus and Dick Plum 2002. They seem to work fine, of course, when they are working where supposed to. For example, Dick Plum is validated in carbonate mostly. And the UCS is as a definition, it is how when you are applying, the UCS is the maximum compressive strength that a rock can withstand without applying any support from the side. So if you have a cylinder of rock and you are applying compression from top and you have no fluid, or you don't have a metal capsulate to support the rock from the side, and the moment the rock collapses, that is your UCS, and it usually collapses at 45 degrees angle from top to bottom. Here I'm showing you the amount of uncertainty that we usually deal with in most of the borehole log-derived equations. So here I computed UCS. I calibrated to 2 points. Do I have a high level of confidence? Of course not. It's only 2 points. I really like to have something here where the rock become more harder, and something here probably at the top just to validate what it is. Of course, that's luxury. We don't always have those. Looking at the second plot, this is all the UCS commercial equations that are provided in a commercial software. And if I want to go and apply them blindly without having core, what looks a very weak, incompetent rock, and another equation, if I don't have the core, would make it look a very strong rock, and then I can give drilling recommendations. And based on those drilling recommendations, a catastrophic events can take place because the whole thing was based on wrong assumptions. Those equations here, they're applied with their default parameters, the way they were published in SPE and ARMA and other organizations. And the fact they failed because they're not applicable to this environment. So if my environment here is offshore Gulf of Mexico, that means it's unconsolidated sand shale sequence. I can't use something that is designed for low porosity. And I can't just use something that is designed for limestone, for example, as it's a more competent, harder to break rock. So I advise you to always be mindful when you are applying equations, because just like any scientist, you can come up with a very nice nonlinear relationship between porosity or UCS. That is because you have so many points that fits that nonlinear regression here. But also there is a very good chance that you are here, that you are toward the very low unconfined compressive strength. And that means there's a higher probability of failing if we always assume we are on the line and we apply the equation, but there's a very good chance we are below it or above it. And above it is not a big problem. That means a more competent rock, but below it, that can be a very challenging thing. So always keep that in mind. Moving to a different topic, the tensile strength, it is how much the rock will withstand pulling. So if you are pulling the rock from two sides, how much the rock will withstand this pulling. And because we're always, most likely we're under compression, and the rock will, because it's supported from the bottom, it will withstand way more compression than pulling. Then simply the tensile strength is used to be a multiplier, or it's computed as a multiplier of the UCS. If you do not have core to validate, you can always go with the industry rough estimate of 0.1. And of course, if you have core, you can always calibrate to that and change the multiplier, or even check your UCS that you are using as an input. The friction angle, I would really like to talk about this one when we talk about more Coulomb criterion. But the friction angle is how the body is, how the rock is resisting the shear failure. And there are so many equations for it. If you have a gamma ray, I would say, and you are in the same channel sequence, or even in a calcite is included, again, you can derive it from a gamma ray correlation, where you just define your friction angle in sandstone 35, and you define your friction angle in a shale anywhere between 17, 18, and 22. And the method based on your shale, how your gamma ray is changing between 75 for shale or more, based on organic, non-organic. And of course, your low gamma ray representing your non-shale formation, it will interpolate and get you a good value. I did not find really big difficulty when it came to the friction angle computations. So far, we talked about vertical stress, overburden or vertical, pore pressure, elastic properties, and rock strength properties that we usually need for our MEM. Here we will talk about the minimum and maximum horizontal stress. Minimum maximum horizontal stress, minimum horizontal stress specifically, it's a measurable quality. So you can measure it from well testing, from a mini frac, from a defit test, from whatever you call it. You can also model the breakouts as well, in that you can capture from an image, or you can talk to your drilling folks and say like, hey, what was your mud weight? Did you have any losses? You didn't. The moment you have a kick in, that is pretty much your minimum horizontal stress, and so on. So there are so many ways. The bottom line, there are so many ways to get a good sense of your minimum horizontal stress. But when it comes to maximum horizontal stress, it has to be referred to or modeled, because we do not have a direct measurement. For example, Schlumberger sonic scanner tool has two models that work for maximum horizontal stress direction and magnitude up to 45 degrees, but they will require tons of inputs, and they will require a very careful study of the variation that happened near the wellbore, and it is an extensive study. The same thing, you can model it using 3D geomechanics modeler, and you can always use, of course, the local knowledge. You know, if you go to the Permian, there are tons of geomechanics engineers that they just know it because they have been doing it for so long. And that is something really nice and always advisable to have if you're working in such a project, to reach out to the community that they have information for you. When we are computing the stresses, there are several models. Two of the most known ones are the Moore-Coulomb, the first one, and the second one is the poroelastic model. For Moore-Coulomb, Moore-Coulomb has a failing criteria when plotting effective stresses on the x-axis and the shear stresses on the y-axis. And if you are in a normal stress regime, then the correlation will be between the effective vertical stress, that means the sigma V minus pore pressure, and the minimum horizontal stress minus pore pressure, and of course, your maximum horizontal stress will be somewhere in between. The line itself defines the Moore Coulomb criterion, and that is when the rock will fail. So on the y-axis, you will have the cohesion value. That's something also observed from core or from the local knowledge, and also the angle, the friction angle, when the rock, that according to this angle, the rock will fail. The higher the pore pressure, the less is the effective stress. That means the circle will move toward the left. That means your rock will fail earlier, as the failure takes place when this circle touched that line created from the cohesion and the friction angle. I personally use this method always with caution, because most likely your maximum horizontal stress that you're trying to solve for is not going to be correct due to the limitation of the method. It's not the software, it's just how the method is meant. But if I do not have enough information about my minimum horizontal stress, this method tends to give you minimum horizontal stress that is less than the actual one. That gives you a safety net of your computations, because you do not want to overestimate the stress. If you really do not have that knowledge, you really need to have a safety net for your computations, or a range. And this is why I like to run this method first before I jump to the second one, which is the poroelastic equation. And the poroelastic equation, it uses those two equations at the bottom based on all the inputs that we have, all the qualities that we have been finding, like Poisson's ratio, Young's modulus, the vertical and pore stress that we have computed so far up to this point, and then multiply that by alpha, which is both coefficient, and two variables that you have is epsilon h minimum and epsilon h max. Those are just the strain coefficients that the method use, and those coefficients. One second, I think there's a question.
Yeah, the question is, do you mind sharing how to accommodate the anisotropy in the elbow section, going from vertical into the horizontal wall? Or
I'm sorry, repeat that one more time.
Repeating that again. One second. Do you mind sharing how to accommodate the anisotropy in the elbow section, going from vertical into the horizontal wall?
Oh, that's a great question, and very challenging actually to accommodate for himself.
Deborah for asking, or in cases where the wall needs to be deviated to avoid some troubling area.
Well, okay. Well, that is very complicated one. So if I want to go back, I'll come back to this slide in a second, but let me come back to one of the first slides here. So here you see that here we are, we're going vertical up to the kickoff point, right? At the kickoff point, we start increasing deviation, and we can either go horizontal and keep it this S shape as it is right now. One factor that determines that, let's say here we don't have shale, this is where we have the shale. One factor that how we can do it safely is to study the bedding angle and also studying the plane of weakness, because the UCS as quality for shale at a certain bed, the UCS will be like a U shape. When you're hitting a bed of shale that is called the plane of weakness, then the rock strength will be at the minimum. That will be that if we hit it at that angle of deviation and the bedding at that degree, then we will have collapses and we will have losses and we may lose the well. But for that, you need a full study of anisotropy. You need 3D mechanical anisotropy modeling. What we do, Schlumberger and had a database of vertical and horizontal compressional slowness, vertical and horizontal shear slownesses, at 0, 45, and 90 degrees. And what we do, we try to combine any, and of course they're basin by basin. So what we try to do, we try to use modeling based on their knowledge, based on this database from 0 to 45 or from 0 to 90. Based on this database, we try to model how the change in vertical and horizontal compressional, vertical and horizontal shear, and from there we try to get the values of TAMU-SPE parameters. And from there, we run 3D the photoelastic model, but instead of using one Poissons and one Young's, we will use two, one for vertical, one for horizontal, and also two alpha, two Bowen coefficients. But this section here is very challenging. Even with the modeling, you can end up, if you're not using a proper database to invert with, you will end up with erroneous results. So another way we do it is that if you are a company X, you had a well that has compressional and shear velocities in the vertical section, and the same well you probably log the curve and also the horizontal section. So we will conduct a full study also using modeling and inversion, and we'll try to get those vertical and horizontal qualities that we need for shear and compressional, and then give you a Thompson parameters and compute the stress based on them. I hope I answered this question properly, because that question is very important, and it's definitely a very challenging topic. I do not see the chat. Okay, great, thank you. Okay. So going back to our maximum horizontal stress, we talked about more Coulomb and the failing criterion. Now we're talking about the photoelastic. So this is a photoelastic model for isotropic rock again. And I think we just I jumped ahead of myself and talked about anisotropy, but we will address it when we come to it. So if let's say you have a minimum horizontal stress that is calibrated. So the way this works, you will need minimum horizontal stress from DFIT. You will need put pressure to be calibrated. You will need Young's modulus and Poisson's ratio as well to be calibrated to core. That will leave you with three unknowns. Those two unknowns are the sigma, the epsilon H minimum, that's for strain, and epsilon H capital, and the maximum horizontal stress. Once you know your stress regime, that you know the order at which where to expect sigma H. That means if you are in normal stress regime, that means sigma H as a magnitude will be less than your vertical stress. And once you have everything else calibrated, you only manipulate or try different epsilons, H, small letter and capital letter, in order to get the maximum horizontal stress. So to a decent extent, if everything else in this equation is known and calibrated, you can say that I do have a very good value for my maximum horizontal stress. So it is almost calibrated. This is an overview of how does the work happen in a commercial software. So you will always start from the overburden by using the extrapolation method or any other derivative method, because they're all pretty much use the same concept. They are just published by different scientists and the geomechanics engineer. From there, you will use your pore pressure, either Bowers or Eaton, or you can probably compute all of them and compare. And after that, we move to the elastic properties. We first compute dynamic elastic properties, static elastic properties, that is just applying the convergent that we talked about. And then computing the UCS, the tensile strength, and then friction angle. That ends the rock strength section and the elastic property. From there, you either apply more Coulomb or the photoelastic model for your minimum and maximum horizontal stress direction. Up to this point, your MEM is done. That's what you need. And from here, you can take it to the next level by doing wellbore stability, sand production management, fracture stability, and landing study, all other kind of, or even stimulation if you want to see based on your stress profile, how would your stress look like. Now coming to the direction, and the direction is very important because it controls a lot of things. One of them is the direction at which we would like to stimulate our well. And when we are planning to stimulate in a specific direction, then we are also drilling in a specific direction, which is usually perpendicular to that. So there are several ways to determine the stress direction for vertical and subvertical wells. And this is where the challenge comes, because those methods are all applicable to vertical and subvertical. For example, if you have an oriented calibers or wellbore images, those two tools can detect borehole enlargements such as breakouts, or in the case of the image, you can see clearly this the stress-induced fractures that are function or quality of a stress-sensitive formations. And using either or both tools, you can have a good idea or very conclusive result about your direction of minimum horizontal stress, which will be parallel to the breakouts, or the maximum horizontal stress, which will be in the direction of the drilling induced fractures. But when we came to deviated wells, we are no longer drilling in the direction of the vertical stress. Now we are actually, the vertical stress will start acting on the borehole and will change the stress distribution around the borehole, because it's affecting it as the borehole deviation increase. And that means that the breakouts that usually are in the direction of minimum horizontal stress, they are not anymore. And the same applies for the drilling induced fractures. It is due to the vertical stress contribution under that deviation. And of course, that contribution will change as the deviation increase and decrease as well. So one slide that I found very useful is this here, based on how can we define the breakouts using caliber readings. It's a very simple approach. When you're using directional calibers or azimuthal calibers, you have 4 arms open during the logging operation. Those arms record 2 different measurements or 2 independent measurements of the wellbore. And if they're both engaged, that means you have a good borehole condition. But if one of them, only one, is reading out gauge, reading a larger value, and the other one is engaged, that means you are in a breakout. This is the essence of how the method works. I wouldn't say it's the most conclusive approach. Sometimes people misread those breakouts coming from caliber, but it's still a good indication of them. If you have, of course, if you have image tool, then yeah, you can clearly see the breakouts and drilling induced fractures by eye, and then you will know for sure, because the imaging tool, it is also azimuthal image, and you'll have a recorded direction in it. So here, after I'm showing you how that is done, after we're defining ovality cutoff, we see that the caliber automatically detected that we have breakouts in this direction. And you might say this is not very conclusive. I don't think this is very conclusive. I really like my results to be within 20 degrees. So here it's ranging from 10 to 330, but sometimes you don't have advanced tools to work with. So bottom line, this is how life goes, right? You don't have always all the luxury of advanced physics and advanced science. From images, it's pure interpretations. Your borehole geologist will do the depth picking. And here I'm just showing you the difference between the breakout and the drilling induced fractures. The breakouts usually on a resistivity image look in a dark color, indicating the conductivity. And that is because this breakout is a small enlargement in the borehole, and this enlargement is filled with fluid And this fluid, if we are in a water-based mud, will be conductive fluid, while the image itself is measuring resistivity in very bright color and the conductivity in very dark color. And due to the tool high resolution, low depth of investigation, you will see it as a very dark color, and they are usually 180 degrees, so from 0 to 180 to 360. So usually the way you would see the breakout and induced fractures, you'll see them at 90 degrees from each other. So you'll see breakout 90 degrees, induced fractures, and of course they're not going to be in the same formation. They will be in different formations. Unless you have a fault or microfault, then yeah, in that case you might have a stressed rotation, and you may find both of them at the same angle, but you need to validate your results with borehole geologists, telling them, hey, is there a fault here? Why they are at the same azimuth. So that's another way to define the direction of both minimum at the breakout direction and maximum horizontal stress at the drilling induced fracture. And you see here that we are almost in 20 degrees. So the resolution or the quality of the answer is better, but you can always integrate the results from both tools, from calipers and images. For coming to the next method of defining the direction of maximum horizontal stress, let's say most companies avoid images as much as they can, because that's the most expensive tool to run and to process. So instead they run a sonic scanner or similar tool from different vendors. And the way the dual fluxural waves or the dual dipole method work is it has two dipole sources that they emit fluxural waves in the borehole. Those fluxural waves are at different frequencies, and the low frequency propagates deep into the formation, and the short or the high frequency propagate very shallow near the surface. And taking this information into a cross plot of frequency versus slowness, we see that the same wave, the fluxural wave that is transmitted under different frequencies and received by different sources, 13 of them, different receivers, 13 receiver for sonic scanner, then you'll have this distribution at low frequency. You will have what represents the part of the fluxural wave that is representing the formation shear, and at the very high frequency you'll have the surface wave. So as we said, it's a dual dipole source. That means we will have two of them. And if your formation is isotropic, then those two dipole recorded waveforms will be overlaying each other. But if you are in a stress-sensitive formation, such as a permeable sandstone, then you will have different in the arrival time, and not only the arrival time, but also the alignment of the fast shear, but before this point, they're both equal shears. There is no fast and slow in isotropic rock. When you move to anisotropic rock, there is fast and slow, and the tool records the direction or the azimuth of the fast shear. So if you are going back to our permeable stress-sensitive formation, we're recording fast shear, and because we are in stress-sensitive formation, we observe this crossover at the high frequency range as a unique signature for the stress-sensitive formations. So if we do not observe this signature, that means it still can be stress sensitive, but not as sensitive. You can be in a shaly. It's not as clean as a pure sand, but this is the signature you would be looking for when you are defining your stress sensitive formations. Once you observe this and you look at the tool azimuth, in this case, because it is the shears are split, one in the direction of the maximum stress, that recorded azimuth is actually the direction of your maximum horizontal stress. And that's how we will define our maximum horizontal stress direction. Here, I don't want to overwhelm you with detail. There is this paper it's called following stress direction from borehole shear anisotropy. It's on ARMA. This is the reference number. The method talks in details how we would define the zones where we think it's stress sensitive. And once we define them, we always look in that plot that I showed you for frequency versus slowness.
Issa, hello. Unfortunately, we didn't see you. Not right now, to be honest. Some reason. Hello?
Yeah, I think he's having network issues.
Let's wait a little bit. Oops, apparently he did. Let's wait till he comes back. Shouldn't be a problem. Ooh.
Hey, do you hear me again?
Yes, you disappeared.
Okay, lovely. Okay, could you please assign me as a host?
And yes.
Please, thank you.
Let me share a screen now.
Okay, let me go back to presentation mode. Okay, can you see my screen, everyone?
Not yet. Just about, yeah.
Should be coming up. Can you see it?
Yeah, can you also assign me as a host again?
Hello, Serhi?
Yeah, I hear you. But for some reason this. Okay. Okay, good. Yeah, I see. Yeah, you can continue.
Serhi, can you see my screen?
Yes, I see a screen, but sometimes for some reason your picture is lagging a little bit, but it's fine. You can continue as of now. So far, so good.
Okay, so going back, I just got the confirmation from Serhi, we are good. So here is we observe the crossover. So we will first define the cutoff zone where we need a formation sand that is stress sensitive with a good borehole condition. Also here we have the recorded azimuth from the fast shear that was recorded in this zone. And also we have the difference between fast and slow because we need an anisotropic. That's we're referring to the difference between the red and blue curves here. That is the anisotropy that I'm talking about. And in the same plot, in the frequency versus slowness plot, we observe that crossover where we have fast shear in red dots and that fast shear become the slower one, and the high frequency showing us the signature that we would expect for stress-sensitive formations. Going back to our workflow, so here we included all the results from calibers in yellow, from the breakouts images, and also from drilling-induced fractures and stress and fast shear azimuths from sonic scanner. And you can see we have a beautiful picture with a complete agreement between all three tools. So this is applicable for vertical and subvertical wells up to 15 to 20 degrees. For sonic scanner, you can still, for the sonic tools, you can still apply it up to 45 degrees with including the shear radial profiling and looking at how this shear is changing at 5 inches or 10 inches or 3 feet from the borehole. But it is also involves a modeling part, and it becomes more, it requires a lot more inputs to work with. So how do you think we would address the stress direction problem if we are in a highly deviated wells? I would really like to see if you guys have any ideas about that, or if you have any work done on this as a part of your grad school. Okay, so I'll tell you, and you probably can ask me later or reply to the chat section. So we will repeat the 3D stress matrix, yes, but you will need a lot of input. But and here we're also trying to solve for the direction more than the magnitude. But that's a good one. That's a good answer. What we'll try to do is we try to have a regional model. First, we'll try to get the knowledge of our stress regime that will define the stress magnitude order for us. Which one is larger? Is it the normal stress? Is it strike slip? It's a fault regime, and so on. Once we have that, we can repeat what we have done for all different tools that I just showed you, and then combine them and see where that's stress. So at the end of the day, you'll have one local stress solution. And according to that direction that you picked from each one of those wells, that can be not representative of the stress. Once you have the R, or the stress regime factor, you can plot them against each other, and they will intersect in 1 point or in 2 points that are 180 degrees apart from each other. That means you have a unique stress solution. But for this kind of work, it's a multi-well study that involves data integration from several wells that cover different deviations, and also cover the same lithology probably at different deviations. So it's more involved work, and but you will end up with a unique stress solution. And here I'm sharing with you a slide about how difficult it is sometimes. So if you're in U.S. land, then yeah, you do have your beddings, you do have your shales, you have an extensive knowledge of stresses, and you probably don't need to spend that much money on it. But if you are, let's say, in the Gulf of Mexico, and I'm showing you as a snapshot from a map of the Gulf with the stress on it. Those directions are the direction of the stress recorded in the Gulf of Mexico. And as you can see, in some of the spots, you have a decent consistency. For example, here you have this well, 2, 3, 4, 5. You have, 4 wells are pointing toward the same direction, give or take. But when it comes to this salt dome here, where they're pointing from 0 to 360 and anywhere in between. The same for this salt dome here. And companies in the Gulf, they spend a lot of money because those are challenging wells to work with. And that's one of the challenges, is depending on you're from the same rig, you're drilling several wells, and you're doing a kickoff at some depth, and you are drilling around that. You are drilling around the salt dome, and as you drill around the salt dome, even though you are on the same on the same platform, the stress rotate around the salt dome, and you will end up with different wells from the same platform, but they are pointing to, or they are under different stress directions. So that is one of the challenges that is related to this kind of environment. So far, we've done everything about mechanical earth modeling, but we always addressed isotropic rock. We always assume that my property is going to be the same in all three directions, and that means that I am pretty much solving for this yellow simple equation here, or this state of stress. But in most cases, you are either here, TIV, or you are orthotropic rock. In a TIV, I have a property that is changing along the depth along the Z direction, and it's the same in two other directions. That is a very good representative of US land shales, where you have the beddings, horizontal and sub-horizontal beds drilled in a vertical well, and then at some point kicked off and went horizontal. The orthotropic type of rock, it is a rock that can combine. A good example would be rock with bedding and also fractures. And so you have a combination of TIV and TIH, and TIH-like kind of rock, and that makes things even more complex. So, and when you're working in the borehole environment and you're using wireline tools to take this information, you're always looking at anisotropy parallel to the tool. That means you're measuring vertical velocity or vertical anisotropy. And as some rocks, like a TIV, might be the same in X and Y, like most of US shales, US land shales, the actual anisotropy, it is between this bed and this bed. That is where advanced measurement and modeling, for example, we at Schlumberger using sonic scanner, we get a horizontal shear for vertical wells. And the horizontal shear is used by modeling one of the waveforms. It's called Stoney waveform. We modeled that Stoney using bulk density and the different algorithm to have an idea about this anisotropy between the dark brown red, the yellow bed, and then the white bed. And that gives us an idea about how my stress profile will look like. So far we built this. We ended up using the photoelastic model, and if our goal is to frag this well, I will talk first about what you're seeing. On the left, you're seeing elemental analysis, and the rock is a combination of quartz and clay, which is like any unconventional. Probably you can also have some calcite in the mix. And on the right side, with a color coded, you have the stress, the minimum horizontal stress. And the red color means a low stress, the blue color means a high stress, and it is scaled from 0.45 psi per foot to 1.1 psi per foot. And as you can see, the color is not changing that much. That means we have a very stress homogeneous rock that is assuming it's isotropic. That means I'm only looking at vertical anisotropy. But taking into account the horizontal anisotropy, this rock that we thought is homogeneous from the stress state actually has a higher stress level. And not only that, what we think that we can frack at one go, if that's our goal, now we have a stress barriers that will contain that fracture only in the red zones and will end with non-optimized completion or frag design. And the photoelastic model that we had earlier and that I showed you the equation become more involved because it has now, we can see, it has now horizontal Young's modulus and vertical Young's modulus. It has the horizontal Poissons and vertical Poissons. And also some of the equations have even horizontal alpha and vertical alpha. Those are very rare qualities to have core for, so you really are running blind for most of the time. That means you have more challenges to calibrate your maximum and minimum horizontal stress. Here I'm referring to the paper that I'm talking about. Here we have elemental analysis done, where I'm hovering the mouse. And the black color here, where I'm hovering the most as well, that is the stress profile that was generated using the photoelastic model for isotropic rock. But the reality is that the rock is not isotropic, and you need to take the horizontal anisotropy into account in order for you to have a realistic stress profile. Otherwise, you're oversimplifying the problem. And this rock here might be hard to frac, maybe because you have more elites. It can be very challenging for you to deal with if you are assuming that this is my stress, but the reality is it's way higher from top to bottom. In conclusion, we're able to build the 1D MEM using the rock density, compressional, and shear slownesses, and calibrate to core data and drilling reports when available. The quality of the 1D MEM is a function of those calibration points and the local knowledge. And finally, we see how oversimplifying the problem by making the wrong assumptions can lead to erroneous results and unpleasant consequences. The next steps will be conducting wellbore stability, or sand management, or fracture analysis. That is something based on the objective or the challenge that is in hands. And also not only build those models, but validate them by comparing their prediction with the previously drilled wells. So for example, if I have wellbore stability model and I want to check the validity of it, I will run it on a well where I have images, and I will check where my images are seeing drilling induced fractures and breakouts, and compare that to my wellbore stability analysis, because I would expect also the mud weight will be too high that led to fracking the formation, unintentionally fracking the formation, exceeding the fracture gradient. Or in the case of a breakout, I would expect that my mud weight is not in the safe window. Most likely, the operators will be okay with a little bit of breakouts here and there, but they really don't like to frac the formation and exceed the fracture gradient. And that's it for me. Thank you so much for listening, and I hope you enjoyed it. I did not make it too fast or too slow for you. And thanks again. I'm more than happy to take your questions.
Yeah, thank you, Issa. Any question, guys? Please write it down in the comment section. No questions. There is a question, one question from me actually. So you mentioned that we cannot measure SH max correctly in indirect ways. There are different indirect methods. Which one do you recommend, and how significant is going to be the difference between those? You hear me? Mm-hmm.
Okay.
Yep.
That's a good question. So the anisotropic model, thank you for it. The anisotropic model is, it's not one thing. It's not like one anisotropy type. There is anisotropy due to fractures, anisotropy due to stress, as we have seen where we have the crossover signature. And also there's an anisotropy due to beddings that is the intrinsic, and that is a part of the shale. And it can be on shallow or it can be in deep formation. So the depth of the formation is not really, has nothing to do with it. With that being said, the tools that we use in the well, they work better in intermediate range of borehole. So for example, 8.5 inch will be optimum for most of the tools, even though they operate on 12.25 and they operate on 6.60 and 6.675. But yeah, in a nutshell, the answer, it's the anisotropy types are different. They're not always the bedding. They can be fractures, stress-induced, or probably the combination of all three. And it can be applicable on all depth, all the range. But thanks again for all the insightful questions.
Issa, do you hear me? Not sure. Apparently not.
How significant the difference is in SH max calculations defined by different indirect method? That's a good question. Okay. I don't want to keep throwing at you those concepts, but let me go back here for 1 sec. So here in Moore Coulomb, if you want to apply Moore Coulomb and you know that your stress regime is normal, what I mean by stress regime is normal, that your in terms of magnitude, the largest stress is vertical, the smallest stress is the minimum horizontal stress, and your maximum horizontal stress is somewhere in the middle. So using Moore Coulomb, most likely your maximum horizontal stress will be off the chart. It will be way larger than your vertical stress. So it's not reliable at all in this case. This is why you come here, you get your minimum horizontal stress and get also with a safety net underneath because it is underestimated in here. You come to the photoelastic, and if you have everything calibrated, then you shouldn't worry that much. It should give you a very good estimation of your maximum horizontal stress. So for example, you calibrate to DFIT, you calibrate to core for the minimum horizontal stress to DFIT, the elastic properties to core, your pore pressure to MDT, and you're good to go. Mm-hmm. You have your maximum horizontal stress. You just play a little bit with your strings. And there are, of course, I'm not saying that they are like, okay, you start from 1 or start from 10 or there are industry standards for the minimum and maximum strains value. So you're not running blind here. I hope I understood your question though.
Yeah. Thank you. Thank you very much for answering that. Any other questions? Okay, I think if you do not have any other questions, I would like to thank you, Issa, for wonderful presentation. Do you hear me, Issa? Because I'm not sure if you follow me. No, unfortunately not.
Oh no, Sergey, I don't hear you.
Ah, you didn't hear me. Okay. Well.
And you're not muted.
Yes, not muted. 1 second.
Can you try the other device?
I can hear you, though, Sergey.
Before?
You can hear me?
Yeah, I can hear you.
Or can anybody else speak? So we make sure that.
Yes.
I can hear you too.
Oh wow! I can't hear Sarkar either. Sarkar, I can't hear you.
Oh.
Wait, Issa, can you hear me?
No, he doesn't apparently.
Oh,
I think
yeah.
I can try to take my headsets off. See if that helps. I can hear you. Whoever's speaking now, I can hear you guys.
Oh,
okay.
Yeah, perfect. Do you hear us now?
Yes, I do hear you
perfect.
very well.
Perfect, great.
I'm sorry if someone asked and I did not answer. Please go ahead and repeat the question. I will do my best.
I actually asked it already in the chat, so I'm good.
Okay, good.
Yeah. Okay, guys, if you don't have any other questions, we're good to go. And thank you, Issa, for your wonderful presentation. And thanks, guys, everybody, to join in this meeting. We will post this video most likely on YouTube, so we can kind of like rewatch it and may come up with other questions to you while reviewing it as well. So
Lovely.
thank
Lovely.
you.
That sounds good.
Thanks a lot.
Thank you.
It was my pleasure, and I hope you enjoyed it all. And good luck, and I wish you a fruitful career both in academia and after graduation.
Thanks a lot, Issa.
Okay, my pleasure.
Mm-hmm.
Thank you.
Okay, have a good one.
Have a good one too.
Okay.